Welcome to this walkthrough of LeetCode problem number 402, remove k digits. In this problem, we'll tackle how to efficiently remove k digits from a number string to produce the smallest possible number. Let's dive in. In this problem, you're given a non-negative integer represented as a string called number, which is made up of digits ranging from 0 to 9. Along with number, you're also given an integer k. The task is to remove exactly k digits from the string number in order to create the smallest possible number. However, there are a few important rules to keep in mind. First, the resulting number should not have any leading zeros unless the number itself is 0. Finally, the output should be returned as a string. For example, you might be given a string like 1432219 and asked to remove 3 digits. We'll explore how to achieve the optimal result in the examples ahead. Looking at the first example, if number is 1432219 and k is 3, the goal is to remove 3 digits in a way that minimizes the resulting number. By carefully removing the digits 4, 3, and 2, we end up with 1219, which is the smallest possible number that can be formed. Notice how we prioritized removing larger digits first, while maintaining the order of the remaining digits. This ensures that the number stays as small as possible. Now, consider another example where number is 10,200 and k is 1. Here, we remove the digit 1, resulting in 0200. After dropping the leading 0, the final result is 200. This demonstrates how we not only remove digits but also ensure the output adheres to the requirement of not having leading zeros. In the third example, if number is 10 and k is 2, we need to remove all the digits in the string. Removing both 1 and 0 gives us an empty result, but since the problem specifies that the output must be 0 in such cases, the function should return 0. This example highlights how the problem handles cases where the entire number is removed. Now, let's go over the constraints. The length of number will always be between 1 and 100,000, and number will only contain digits from 0 to 9. Additionally, the value of k will always be a valid non-negative integer, ranging from 0 to the length of number. These constraints ensure that the input is well formed and within a manageable size for computational purposes. There are also some important edge cases to consider. First, if k is equal to the length of number, the result should always be 0, since you're required to remove all the digits. For instance, if number is 1234 and k is 4, the output is simply 0. Another edge case occurs when number consists entirely of zeros. Regardless of how many digits you remove, the result will always be 0. For example, if number is 0000 and k is 2, removing any 2 zeros still leaves you with 0. Finally, if k is 0, meaning no digits are removed, the output should be the original number itself. For instance, if number is 5678 and k is 0, the result remains 5678. Considering these edge cases ensures that the solution is robust and handles all possible scenarios effectively. When approaching this problem, a naive solution is to try all possible ways to remove exactly k digits from the number and compare all the resulting numbers to find the smallest one. While this brute force approach guarantees the correct result, it becomes computationally expensive very quickly. The reason is that generating all combinations of k digits to remove from a string of length n has a time complexity of approximately n to the power of k. For large inputs, this is simply infeasible. To address this, we can turn to an optimized approach, a greedy algorithm that uses a stack. The key insight here is that the smallest number is achieved by removing digits that disrupt the increasing order of the number. For instance, in the number 1432219, if we need to remove 3 digits, removing 4, 3, and 2 in that order leaves us with the smallest possible result. The greedy strategy involves iterating through the digits and using a stack to dynamically build the smallest sequence. By comparing the current digit with the top of the stack, we can decide whether to remove the top element, effectively reducing k, to ensure our sequence remains as small as possible. This strategy can be broken down into clear steps. First, we use a stack to store the digits of the resulting number. As we traverse the digits of the input number, we compare each digit with the top of the stack. If the current digit is smaller than the top of the stack and we still have digits left to remove, we pop the top of the stack and decrement k. After processing all digits, if k is still greater than 0, we remove the last k digits from the stack. Finally, we convert the stack into a string, ensuring we remove any leading zeros. This approach is efficient, with a time complexity of O(n), since each digit is pushed and popped from the stack at most once. The space complexity is also O(n), due to the stack. While sorting the digits might seem like another potential solution, it doesn't guarantee that the resulting number will respect the sequence constraints of the original input, making it less suitable for this problem compared to the stack-based method. The greedy algorithm with a stack is the strategy of choice because it balances efficiency, correctness, and simplicity. By dynamically adjusting the sequence of digits while maintaining their original order, the stack allows us to build the smallest possible number in an intuitive and methodical way. Unlike brute force, this method avoids the exponential growth in complexity, and unlike sorting-based methods, it adheres directly to the constraints of the problem. A few key insights drive the effectiveness of this approach. The smallest number is achieved by prioritizing digits with smaller values while ensuring their relative order is preserved. Additionally, removing digits that disrupt ascending order minimizes the result, and the stack provides a natural mechanism to manage these removal decisions incrementally. When comparing the trade-offs, brute force is correct but computationally prohibitive, sorting is simple but requires additional work to maintain validity, and the stack-based algorithm stands out as the optimal solution. In terms of complexity, the greedy algorithm with a stack is highly efficient. The time complexity is O(n), where n is the length of the input number, because each digit is pushed and popped from the stack at most once during the process. The space complexity is also O(n), as the stack stores a subset of the digits from the input number. This ensures that the solution is not only correct but also scalable, making it well suited for handling larger inputs effectively. The problem we're solving is to remove k digits from a given number, represented as a string, to form the smallest possible resulting number. The result should also avoid any leading zeros, and if all digits are removed, we simply return 0. First, let's consider the brute force approach. This method generates all possible combinations of the number with k digits removed, converting each combination into a number and keeping track of the smallest. However, this approach is highly inefficient due to the sheer number of combinations. For a string of length n, the number of combinations is given by c, n, k, which grows exponentially. This results in a time complexity that's infeasible for large inputs. To address this inefficiency, we turn to a more optimal solution, a greedy approach using a stack. This method allows us to iteratively construct the smallest possible number while efficiently managing the constraints of the problem. To implement the greedy approach, we begin by initializing an empty stack. This stack will be used to build the smallest number incrementally while maintaining the correct order of digits. As we iterate through the digits of the input number, we compare each digit with the top of the stack. If the current digit is smaller than the top of the stack and we still have digits left to remove, we pop the top digit from the stack. This ensures that we are removing larger digits when possible to minimize the resulting number. After removing digits, we push the current digit onto the stack. We also decrement k for each digit removed, as it tracks the remaining number of digits we are allowed to eliminate. Once all digits have been processed, if k is still greater than 0, we remove any extra digits from the end of the stack. Finally, we convert the stack into a string, remove any leading zeros, and return the result. If the resulting string is empty, we return 0 to handle cases where all digits are removed. The greedy approach works because of some key insights. First, the greedy choice is to always remove the largest possible digit from the left while traversing the number. This ensures that the resulting number is minimized. The stack plays a crucial role here, as it allows us to efficiently add and remove digits while maintaining the correct order. By pushing only the digits that contribute to the smallest number, we avoid unnecessary comparisons and operations. There are also important edge cases to consider. If k is greater than or equal to the length of the input number, we should return 0, as all digits are removed. Additionally, we need to handle leading zeros in the result, ensuring they are stripped away to form a valid number. For very small inputs, such as a single-digit number with k greater than 0, the result also defaults to 0. These insights guide the algorithm to handle both typical and edge cases effectively. To implement this algorithm, we rely on two primary tools, the stack and string manipulation. The stack is used to store the digits of the resulting number temporarily. It enables efficient removal and addition of digits as we process the input from left to right. By maintaining order and allowing us to remove undesirable digits, the stack ensures that the resulting number is minimized. Once the digits are finalized in the stack, we use string manipulation to convert the stack into the required output format. This involves simply joining the digits together and removing any leading zeros to ensure a valid result. The key operations involved are pushing a digit onto the stack, popping the top digit if a smaller digit is encountered in k permits, and finally converting the stack into a string while cleaning up any leading zeros. These operations are simple yet powerful, making the entire algorithm both efficient and easy to implement. The time complexity of this approach is O(n), where n is the length of the input number. This is because each digit is pushed and popped from the stack at most once, making the process linear. The space complexity is also O(n), as the stack can hold up to n digits in the worst case. To illustrate the algorithm, consider the example where the input number is 1432219 and k is 3. Starting with an empty stack, we process each digit. The stack evolves as follows: 1 is pushed, followed by 4. When 3 is encountered, 4 is popped because 3 is smaller. Similarly, 2 replaces 3. The remaining digits are added or removed based on their value and the remaining k. After processing all digits, the stack contains 1219. Since no extra digits need to be removed, we directly convert the stack into the result, yielding 1219. This walkthrough demonstrates how the algorithm efficiently handles digit removal to produce the smallest possible number. Here, we define the removeDigits function within a class called solution. The function takes two inputs, number, a string representing the number, and k, the number of digits we need to remove. We start by handling a simple edge case. If k is equal to the length of number, it means we need to remove all digits, so we directly return 0. Next, we initialize an empty list called stack, which will help us construct the smallest possible number. The main logic involves iterating through each digit in the input string. At each step, we check if the stack is non-empty, if there are still digits left to remove, and if the top digit in the stack is greater than the current digit. If all these conditions are true, we remove the top digit from the stack and decrement k by 1. This ensures that we are removing larger digits to make the resulting number smaller. After this check, we add the current digit to the stack, building the number incrementally. Finally, if we haven't removed enough digits after the loop, we pop additional digits from the stack until k becomes 0. This ensures that the total number of digits removed matches the input k value. Once we have constructed the stack, we convert it back into a string using join, and we also use lstrip 0 to remove any leading zeros from the result. This step ensures that the output is a valid number without unnecessary padding. If the result becomes empty after removing leading zeros, we simply return 0, since an empty number is equivalent to 0. This concludes the implementation, as the function now returns the smallest possible number after removing exactly k digits while maintaining the order of the remaining digits. Here, we start by importing the necessary Java utility classes and defining our solution class. The method removeDigits takes two inputs, a string number representing the number, and an integer k representing the count of digits to remove. First, we handle a critical edge case. If k equals the length of the input string, it means we need to remove all digits. In this case, the result would simply be 0, so we return it immediately. Next, we use a stack, implemented as a deque, to help us determine which digits to keep. As we iterate through each character in the number string, we compare the current digit with the top of the stack. If the top digit in the stack is greater than the current digit and we still need to remove more digits, we pop the stack and decrement k. This ensures that we remove larger digits earlier, favoring smaller digits to achieve the smallest possible result. After handling such cases, we add the current digit to the stack for further processing. Now, if there are still digits left to remove after the initial iteration, we continue popping the stack from the end until k becomes 0. Once this is done, we move on to constructing the final number. We create a string builder and append each character from the stack to it, ensuring we maintain the correct order. Then, we address another important detail: leading zeros. Using a while loop, we delete any zeros at the beginning of our result string. If the string becomes empty after removing these zeros, we return 0 as the final result. Otherwise, we convert the string builder to a string and return it, which represents the smallest possible number after removing k digits. This approach ensures that the solution is both efficient and concise, handling all edge cases appropriately. To solve the problem of removing 2 digits from the number 1432219, we start by initializing an empty stack and setting the remaining digits to remove k to 2. The first digit encountered is 1. Since the stack is empty, there are no comparisons to make, and we simply push 1 onto the stack. At this point, the stack contains just 1, and k remains 2. Next, we process the digit 4. The stack is not empty, and the current digit 4 is greater than the top of the stack, which is 1. To maintain a non-decreasing order in the resulting number, we push 4 onto the stack. The stack now contains 1, 4. Moving on to the digit 3, we see that 3 is less than 4, the top of the stack. To minimize the number, we pop 4 from the stack and decrement k by 1, leaving k as 1. We then push 3 onto the stack, resulting in 1, 3. For the digit 2, since 2 is less than 3, we again pop the top of the stack, 3, and decrement k to 0. With k now 0, we push 2 onto the stack, leaving us with 1, 2. Now that k has reached 0, we no longer need to remove any digits. For the remaining digits in the number 2, 1, and 9, we simply add them to the stack. This gives us the final stack of 1, 2, 2, 1, 9. To build the result, we convert the stack into a string, yielding 12,219. Since there are no leading zeros to remove, the final result remains 12,219. Thus, the output for this example is 12,219. In the next example, we aim to remove 3 digits from the number 10,200. We start by initializing an empty stack and setting k to 3. The first digit, 1, is processed. Since the stack is empty, we push 1 onto the stack. This leaves the stack as 1, with k still at 3. For the next digit, 0, we observe that it is less than 1, the top of the stack. To minimize the number, we pop 1 from the stack and decrement k to 2. We then push 0 onto the stack, resulting in 0. The digit 2 is then processed. Since 2 is greater than 0, we push it onto the stack, which now becomes 0, 2. When we encounter the next 0, it is less than 2, so we pop 2 from the stack and reduce k to 1. Finally, we push 0 onto the stack, giving us 0, 0. The next digit, another 0, is processed. Since 0 is equal to the top of the stack, we simply push it onto the stack. This results in 0, 0, 0. Now, with k equal to 1, we must remove one more digit to satisfy the requirement. We pop the top digit, 0, from the stack, leaving 0, 0. To build the result, we convert the stack into a string, yielding 2000 foot. After removing the leading zeros, the final result becomes 0. Therefore, the output for this example is 0. In the final example, we need to remove one digit from the number 10. As always, we begin by initializing an empty stack and setting k to 1. The first digit, 1, is processed. Since the stack is empty, we push 1 onto it. The stack now contains 1, and k remains 1. For the next digit, 0, we observe that it is less than 1, the top of the stack. To minimize the result, we pop 1 from the stack and decrement k to 0. We then push 0 onto the stack, leaving 0. With no more digits to remove, we build the result by converting the stack into a string, giving 0. After removing any leading zeros, the result remains 0. Thus, the output for this example is 0. To analyze the time complexity of this solution, we can break it down into distinct steps. First, the for loop iterates through all the digits in the string number, which has a length of n. Each iteration involves basic operations like comparing digits or appending to the stack, all of which take constant time. This loop runs exactly n times. Next, we have the inner while loop. This loop pops digits from the stack whenever the top of the stack is larger than the current digit and k is greater than 0. Importantly, each digit in the input is pushed onto the stack at most once and popped from the stack at most once. So, the total number of iterations of this while loop across the entire algorithm is also bounded by n. Additionally, after processing all the digits, if there are still digits left to remove, k greater than 0, we perform another while loop to pop up to k digits from the stack. Since k is always less than or equal to n, this step is also linear in complexity. Finally, constructing the result string by joining the stack and removing leading zeros with .strip 0 involves linear time operations. Each of these steps contributes O(n), leading to an overall time complexity of O(n). Now, combining all the steps we discussed, the total time complexity is O(n) for the iteration, O(n) for the while loop, O(n) for removing extra digits, and O(n) for the final string construction and cleanup. Adding these together gives O(n) plus O(n) plus O(n) plus O(n), which simplifies to O(n). So the overall time complexity of the algorithm is O(n), where n is the length of the input string number. For space complexity, the primary contributor is the stack used to store digits. In the worst case, when no digits are removed, the stack will store all n digits of the input string, requiring O(n) space. Additionally, the result string constructed at the end will also, in the worst case, have a length equal to n, requiring O(n) space as well. Since no other significant auxiliary data structures are used, the total space complexity of the algorithm is O(n). To understand how the algorithm performs in different scenarios, let's break it down into best, average, and worst cases. In the best case, the digits of number are already in non-decreasing order, meaning the while loop inside the for loop rarely executes because the stack is always in the correct order. Even in this ideal scenario, the algorithm still processes all n digits, so the time complexity remains O(n). In the average case, the algorithm processes each digit once, and some digits are removed as needed. The while loop will execute intermittently but not excessively. Here, the total work is still proportional to n, resulting in an O(n) complexity. The worst case occurs when the digits are in strictly decreasing order. In this scenario, every digit must be removed from the stack to satisfy the conditions of the problem. This means the while loop will execute k times, but since k is bounded by n, the total time remains O(n). Overall, regardless of the case, the algorithm consistently runs in O(n) time. Finally, let's compare this optimized solution to a naive approach. A brute force method would involve generating all possible numbers by removing k digits, comparing them, and selecting the smallest. Generating all combinations requires O, C, N, K time, where C, N, K is the binomial coefficient, and comparing each combination adds additional computational cost. This results in exponential complexity, which is infeasible for larger values of n. In contrast, the stack-based greedy algorithm we implemented simplifies the problem to linear time, O(n), by ensuring that only necessary digits are removed. This drastic improvement is achieved by observing that each digit is pushed onto the stack at most once and popped at most once, resulting in a total of O(n) stack operations. All other operations, such as comparisons, joining the stack, and stripping zeros, are linear with respect to n. Therefore, both the time and space complexity of the optimized algorithm are O(n), making it significantly more efficient than the naive approach. When solving this problem, there are several common mistakes that can trip you up. First, ignoring leading zeros in the result is a frequent error. For instance, if your result is 00123 instead of 123, this violates the problem constraints since leading zeros are not allowed unless the result is the single-digit 0. To fix this, you can use string manipulation techniques or explicitly handle cases where leading zeros appear after removing digits. Another mistake is removing digits in the wrong order. Some solutions remove digits greedily without considering the long-term impact, which can prevent forming the smallest possible number. For example, removing a smaller digit too early might lead to a suboptimal result. The solution here is to use a stack-based or monotonic approach to ensure digits are removed strategically. Lastly, overcomplicating the brute force approach is a pitfall. Generating all combinations of k digits to remove can result in increased runtime and bugs if not implemented carefully. Leveraging tools like Python's itertools for combination generation can simplify this process and reduce complexity. Now, let's discuss some additional challenges you might encounter. Misunderstanding edge cases is a common oversight, especially when k equals the length of the number. In such scenarios, the result should be 0, but this is often forgotten. The solution is simple: explicitly check for this edge case at the beginning of your function. Another issue is ignoring input constraints. For example, with extremely large inputs where the length of number approaches 10 to the power of 5, inefficient algorithms can fail. To avoid this, ensure your approach adheres to the required time complexity, such as O(n). From an interview perspective, there are some key insights to keep in mind. This problem evaluates your ability to balance greedy strategies with global optimization. Using a stack to remove digits while maintaining the smallest number is a critical pattern. Testing edge cases like number equals 10, k equals 1 resulting in 0, or number equals 12,345, k equals 5 also demonstrates thoroughness. Additionally, be prepared to discuss trade-offs. While brute force methods have exponential complexity, optimal approaches like the stack-based solution achieve linear time and handle large inputs efficiently. Communicating why your solution is scalable can impress interviewers. This problem also connects to several other challenges on LeetCode, making it a great opportunity to deepen your understanding of related concepts. For instance, LeetCode 3.16, Remove Duplicate Letters, uses a similar stack-based approach to maintain the smallest lexicographical order. The current problem, LeetCode 4.02, focuses on removing digits to form the smallest number, so it directly ties into our discussion. LeetCode 3.21, Create Maximum Number, takes a different perspective, asking you to combine numbers from two arrays to form the largest possible number, which introduces a complementary challenge. Lastly, LeetCode 10.81, Smallest Subsequence of Distinct Characters, is another variation where you remove characters while preserving lexicographical order. Exploring these problems can help solidify your understanding of stack-based strategies and their applications. Finally, let's look at some alternative approaches to solving this problem. The brute force method involves generating all possible combinations of removing k digits and finding the smallest valid result. While this approach is conceptually simple, it is computationally expensive with a time complexity of O(n) to the power of k, making it suitable only for small input sizes. On the other hand, the stack-based greedy approach is the most efficient. Here, you use a stack to iteratively decide whether to keep or remove each digit, ensuring the smallest number is formed. This approach has an optimal time complexity of O(n), but it requires careful implementation to handle edge cases properly. Another option is recursive backtracking, where you explore all paths for digit removal and track the smallest result. While this approach can be more intuitive and educational, it is less efficient than the stack-based solution and is best reserved for smaller inputs or learning purposes. Each of these approaches has distinct trade-offs, so it's important to choose the right one based on the problem constraints and input size. Great work! We've covered the remove k digits problem, exploring an efficient stack-based solution. Remember the importance of edge cases and the power of greedy algorithms. Thank you for watching, and don't forget to like and subscribe for more content like this. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!